Hello everyone, I am Seshavidya, working as Associate Professor in the Department of Electronics and Communication Engineering at R.M.K College of Engineering and Technology. So today we are going to discuss magnitude comparator. What is magnitude comparator? So magnitude comparator is basically a combinational circuit. So as the name implies, this comparator which will compare two numbers. Okay, so let us consider A and B. If we compare any two numbers, there are only three chances. So what are they? So the two values or two numbers, it may be equal, or it may be less than that of the other, or it may be greater than that of the other one. So these are all the three chances. So based upon this concept, here what we are going to do is we are going to design a magnitude comparator. If we compare this, that is if we compare two values, it may be of 1 bit, 2 bit, 3 bit, 4 bit. So for example, here today we are going to design a 2-bit magnitude comparator. So this is a block diagram of magnitude comparator. I am taking two values A and B of 2 bits each. So as I told you, what are the outputs? A may be greater than B, or A is equal to B, or A less than B. So these are all the three chances. So based upon this concept, we are going to truth table first. So this is the truth table. So I'm considering, as I told you, A, so which will have 2 bits. Again this B, which will have 2 bits. And outputs are three outputs: A greater than B, A equal to B, A less than B. So I'm considering, so totally how many input variables now? So I'm just naming it as A1, A0, B1, B0. So totally if you just look into this one, which will have the four variables. So if there are four input variables, we know that we can just write that binary combinations from 0 to 15. So what's the formula? Formula is 2 power n, small n. So that small n indicates number of variables. So how many number of variables? 4. So 2 power 4 is 16. So which means it will have the input combinations from 0 to 15 in terms of decimal. So that 0 to 15 we can just write it in terms of 4-bit equivalent. So from 0 to 15. So first you have to construct the input side. That is, first you have to fill up the input columns. That is A1, A0, B1, B0. Now we can just compare. Now we are going to compare. By comparing this one, we are going to write the outputs. So if you just look into this one, A is nothing but 0, 0. Why? Because it's a 2-bit value. And B is nothing but again it's a 2-bit value, 0, 0. Compare this one, 0, 0. And here also it is 0, 0. So if we compare both these values, and we can say that both are equal. So which means what? A is equal to B. So that we can just put that A is equal to B as 1. The remaining outputs are 0. Similarly, second value. So what is the second value? A value is 0, 0, but B is 0, 1. So by comparing this 0, 0 with 0, 1, obviously which is greater or which is lesser? So this A is less, or we can say that is B is greater. So we can say that A is less than that of B. So where is A less than B? The third column, that should be is equal to 1. The remaining outputs are is equal to 0. So similar way we have to compare both A and B values. So wherever it is, whether it is A is greater than B means you have to put it as 1. Suppose if both the values are equal, then we can just put A is equal to 1, A is equal to B as 1. Suppose if A is less than that of B, then we can just put that A is less than B is equal to 1. So similarly, we can just fill up this output columns, all three columns like this. Okay. Now, after completing this truth table, obviously, by using K-map, we can able to find what is the final expression for, that is Boolean expression for A greater than B, A is equal to B, and A less than B. So for that, we are going to use the K-map. So what type of K-map we have to use? Which means there are types of K-maps. It may be in 2 variable, 3 variable, 4 variable, 5 variable, and so on. So that type of the K-map, we have to find it from the number of input variables. According to this truth table, how many number of input variables? 4 input variables. So obviously we have to use 4 variable K-map. So first we are writing this canonical form from the truth table. So if you want, you can just write the canonical form like this. What is A less than B, greater than B, A is equal to B. Write it in a canonical form. Or otherwise, straight away you can just represent this truth table in the K-map. So it's your wish. So I'm just, for simplicity, I'm just writing it as f of, that is function of A less than B, that is equal to, where is where A less than B, that is the last column. Wherever that A less than B is equal to 1, the corresponding min term you have to represent here. So say for example, A less than B is equal to 1 for the combination 0, 0, 0, 1, which is equivalent to what? 1. So we are writing this 1. And again this A less than B is equal to 1 for the combination 0, 0, 1, 0, which is nothing but 2. So we are writing this 2. And then which is also is equal to 1 for the combination 0, 0, 1, 1, which is nothing but decimal equivalent of 3. So we are writing 3. And then this A is less than B is equal to 1 here. So what is this combination? 0, 1, 1, 0, which means what? 6. So we are writing here. Again, and this is equal to 1 for the combination 0, 1, which is equivalent to 7. And again this A is less than B is equal to 1 for the combination 1, 0, 1, 1, which is equivalent to 11. So likewise we are writing canonical form for A less than B, A greater than B, and then A is equal to B. Now you can just represent the same thing in your K-map. As I told you, since there are 4 input variables, so obviously we have to use 4 variable K-map. So what is your inputs? A1, A0, B1, B0. We have to write it in same order. A1, A0, B1, B0. And then we are writing this binary notation for the K-map. And we have to represent this 1, 2, 3, 6, 7, 11. If you know the number system, straight away you can just represent in your K-map. And then we can just do the grouping. Obviously, this 4, that is squad, and then this 2 by using wrapping around from top to bottom. So which will have the pair grouping, and again this 2, again we will have the pair grouping. Now for all these 3 groups, we have to write the expression. That will be the next step. So that we can write for all 3 groups, we can just write the expression. Now this is the expression for A less than B alone. Similarly, we have to do it for A greater than B and A is equal. So now for A greater than B, so this is a representation in your K-map, and as usual we can just do the grouping, and from this grouping we can just able to write the min terms. We are writing in terms of SOP. Similar way, A is equal to B, so all single ones as a group, so you have to write that all 4 min terms, and we can just simplify it. Finally we'll be getting it as f of A is equal to B is equal to A naught x nor B naught into A1 x nor B1. So likewise we can just write the equation. Now obviously what is the last step? Since we got the all 3 expressions, that is all 3 output expressions, A less than B, A greater than B, and A is equal to B. Obviously now we can just draw the logic diagram. So likewise, we can just able to construct 3-bit, even 4-bit magnitude comparator. Okay, fine. So far we discussed this design of magnitude comparator, how to design the 2-bit or 3-bit comparator. So now we have discussed 2-bit magnitude comparator. What is the purpose? What is the application where we can just use this comparator? That is, we'll be using that CPUs, no? Okay, central processing unit, and even that microcontrollers. So there we will be using that comparator. What is the purpose of comparator and that microcontroller and that CPU is that? So that physical quantities like temperature, speed, pressure, that can be represented in terms of binary values. So that binary values that can be compared with the reference value available. So that can be done only by using this comparator circuits. So that is a real-time application of comparator. Okay. So I hope you understood what is that magnitude comparator and how to design 2-bit magnitude comparator. Okay. Thank you.